The readings this week included the treatise by Boris Zlotin and Zussman on directed evolution. I also had a chapter of a book that I had written recently with a colleague about the future of mechanical circulatory support, and if you've read it, you'll see that it's based heavily on directed evolution. And it's there to illustrate both a contemporary example of the theory and just to also illustrate that I do practice what I preach. I actually do use this gainfully in my work. What I did not share with you was yet another more recent report by Boris and Alla, which just goes into really deep detail. If you are really fascinated by the topic, I would be happy to share that with you. I'd like to start by putting directed evolution in the context of everything we've learned this semester and TRIZ in general. Remember that TRIZ is based on 4 key findings. There is a very particular definition of inventive problems in terms of contradictions, that there are such a thing as levels of invention, that inventions do not develop haphazardly, but there are patterns that have been studied that can be applied to new problems. And then there's something that we really have not touched upon, which is patterns of evolution, taking technology one step further. It's based on 3 main premises. We learned 3 really important concepts in this course. The first was ideality, contradictions, and then a system approach to inventive problem solving in a concerted, conscious manner. There are 4 tools within the software that you receive. The first is the Innovation Situation Questionnaire, Problem Formulator, and then everything kind of in between, the algorithm for inventive problem solving. What we did not study, but for good measure, is part of the toolbox, is something called substance field analysis, which I thought was just a little too advanced for this course. There are 7 knowledge-based tools within the portfolio, and we really only studied 2 of them in detail, the 40 principles and the separation principles. However, the other elements are present in the software, and you may have discovered them on your own. You're also free to discover them on your own. And then there are 3 main applications. There's the Inventive Problem Solving toolbox. There's Anticipatory Failure Determination, which we learned a couple of weeks ago. And then this third tool, which is kind of the natural extension of the 2 previous tools, is directed evolution. So not just solving a problem and anticipating possible failures and hazards that may appear as a result of solving the problem, but taking it to the next level, inventing the future generation of the technology. I hope you've noticed that as you study the outline within the Innovation Workbench, that each of the headings and each of the steps align relatively well with the tools and the lectures that we've covered this semester. For example, the criteria for selecting solution concepts is what the objective tree lecture was about. Developing concepts, that's why we learned contradiction diagrams and the 40 inventive principles and the separation principles. Combining ideas into concepts, we studied a number of different approaches, including the analogies approach. Meet criteria for evaluating concepts, that's the weighted objective analysis lecture. Then revealing and preventing potential failures, that was the hazard analysis and the anticipatory failure determination lecture. And then finally, kind of buried in the background, is applying patterns and lines of evolution, planning for the future. And that's really what the directed evolution algorithm is all about, and that's where we are today. Now, within Innovation Workbench, they have what I consider to be a light version of directed evolution. And you can see in the right panel that they have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different approaches and tools that can be followed. But from your reading, you may remember that there's 100 pages worth of theory that goes behind their ever-evolving directed evolution. But this should give you a good idea of the power of the tool and how to apply it in your project and in your practice. I'd like to begin by returning to the innocuous paperclip. Remember, it was a topic of one of the chapters in Steve Vogel's book that we had studied several weeks ago. And you'll also remember that one of the take-home messages was the incremental improvements that was involved over 100 years' time to evolve the modern-day paperclip. You might also remember some of the background history that he provided, namely the fact that before paperclips were used, they had used pins to put stacks of paper together. He also alluded to the fact that the principle of the paperclip involves an elastic metal, relates back to or involves the theory of Hooke and his principles of elasticity. You'll also remember that the paperclip was really not a possible or feasible product until the Industrial Revolution and the 18th century division of labor. He even alluded to a description of how pins were made in Adam Smith's book Wealth of Nations. And in 1830 was the first pin-making machine was described. So the point being is that the origins of something as simple as a paperclip required several other events and technologies to come into existence. But once those predicates were in existence, then all of the subsequent steps were possible. And one of the themes of directed evolution is that you can make these future events take place and you can create the next generation of a technology if you can just recognize the potential resources and opportunities for evolution. Here's a more contemporary example, namely a USB flash drive. I wanted to try to trace the origins or the family tree of the USB flash drive, just to get an idea of the sequence of events and the predicate technologies that were necessary for this invention to come into existence, which then subsequently had profound effects on our lives. It reflects a saying that a friend of mine once shared with me: before you can do something, you've got to do something else. So I went to the literature and found the first reference of the USB drive. It was dated 2000 in November. The invention was actually filed in April of 1999 by two investigators from this Israeli company, M Systems. When I think of breaking down the technology, what is a USB flash drive? Well, it consists of memory, which is made of silicon. It has an enclosure, and it has a connector, and that's pretty much all there is to it. The memory, in turn, is comprised of transistors. They weren't invented until 1947. And for transistors to have been invented, it required the development of semiconductors. Semiconductors required methods for mining and purifying silicon and the required doping agents like arsenic and gadolinium. But between 1947 and 1999, a lot of other things had to happen, like miniaturization of memory, the mass production of semiconductors, so that we today can buy a 16 or 32 gigabyte memory chip for $20. We also needed the existence of the USB protocol, and etc. So this is somewhat discoverable by looking at the prior art, which I did in a very limited study. I just went to some examples of the referenced patents from this original patent. It led me to a somewhat recent patent that was regarding the memory architecture, which was necessary for the USB drive to come into existence. That led me to something related to the USB bus, which was also dated 2000. There are a lot of events that happened rather quickly in sequence. That takes us back, though, to about 1989, in which the invention of semiconductor memory was invented. And following back yet further, the existence of metal oxide silicon semiconductor storage, 1978. That in turn was built on technology of random access memory, 1970. So the take-home message is that every new invention is built on the shoulders of some previous invention or inventions or predicate technologies. And we can either accept this as a passive observer, assuming that other people are those that do the inventing, that it's a matter of luck and the chance and the brilliance, or we can recognize that there are actual patterns of invention, and then when the circumstances and the resources exist, we can actually make the next generation, the next invention come to life. So that's one of the tenets of this TRIZ postulate of directed evolution, that the patterns are revealable or learnable from the researching the history of technology, markets, and society, and then using those patterns, we can purposely use them for system development without a lot of trial and error, which you might remember from your reading assignment was one of the characteristics of the first revolution, where inventions were kind of made more so by accident than by science or through an algorithm. So one of the observations of Altshuller was that systems evolved in 5 stages, or at least he defined 5 stages. So initially, the system doesn't exist, but the important conditions for the emergence are being developed. And that's that critical moment where if you're the first to recognize the opportunity, you can be the first to make a breakthrough in the technology. So the second, arguably the first stage of invention is when the new system appears, and is due to some usually high-level invention. And typically, it takes some period of time for a new technology to be adopted. There are always skeptics and naysayers. There are, of course, counterexamples. But typically, the growth is somewhat slow at first. But then, somewhat exponentially, society begins to recognize the value of the new system, and the growth takes off. At some point, either the resources are exhausted, or the demand is exhausted, or the market is saturated, and the sales or the acceptance or the growth diminishes. So you can think something very simple like the iPhone. The iPhone 1, once it was distributed far and wide, if there wasn't an iPhone 2 or an iPhone 3 or 4 or 5, Apple would be in trouble because they would have already exhausted the demand. So when that happens, that first system begins to decay, and usually another system comes in to take its place. And then this last stage, stage 5, begins if the existing system is not completely replaced by the new one, as the existing system still has a limited area of application. So arguably there will always be a need for a typewriter or for carbon paper, even though it has been greatly supplanted by word processors and fax machines and the like. Just an illustration from my own experience about this so-called S-curve is shown in the history of heart transplantation. The first heart transplant was performed in South Africa by Christian Barnard, 1967. And you can see that there was initial interest, and a handful of we'll call them copycat procedures were performed. They then recognized serious limitations, namely with regard to rejection. And it took quite a long time for society or for this community to recognize the benefit. I'll confess that in the area of 1980 to 1983 or so, scientific discovery of anti-rejection drugs is what really triggered the rapid growth. But then you can see that the curve flattens out in around the year 1990. And in the year 2013, the number of heart transplants performed per year is roughly around 3,000. It has flattened out because we have exhausted the supply. And it's a perfect example of a system that has experienced an S-curve and can go in any number of directions, but most likely down as new technologies will take its place. Okay, another system that maybe you can relate to is, let's take the telephone. So at some point, telephone didn't exist. There was some um, necessary technologies such as electricity and wiring, and telegraph was in place, but the telephone itself didn't exist. Alexander Graham Bell, you know the story, invented the first telephone. It existed in a laboratory. It really wasn't anything that anyone used. There wasn't the infrastructure or the network. But once society recognized the value of the system, it didn't take very long at all for a network of phone lines and mass production of telephones to come into existence. At some point, though, the wired telephone became less and less fashionable. And I know that today there are a lot of households that don't even have a wired telephone. They rely on their wireless telephone. And following this same kind of logic, we have to imagine or accept or have faith that there is yet another technology that is waiting for us in the future that will take the place of the telephone. It's maybe hard to imagine because you maybe believe that we've reached this plateau where there's no possible future improvement. We've crammed everything we can into the smartphone. How could it ever be any better? But as we had discussed in our second class, there's a lot of things that could be made better, and it's inevitable. Okay, another quick example of audio recording. So in the early days of Thomas Edison, he had invented this wax cylinder that had actually reasonably good success. There are a lot of wax cylinders that were sold and still exist today, for that matter. It was replaced by the vinyl disc, and then the wax cylinder fell by the wayside. Wire recording came into play that superseded the vinyl disc in some respects. Reel-to-reel tapes were very popular in the 70s and 80s, but they had their limitations, and they were awkward and sloppy. They were replaced by the 8-track tape, which was convenient but also rather awkward and had its limitations. I will reveal my age and say that I had many a cassette that was eaten by my cassette deck. And these were very popular for many, many years. And you'd go into a store that had nothing but cassettes in them. Today you can't find a single cassette. And surprisingly, DVDs that came into play just recently are beginning to see the end of their life cycle because they're being replaced now by digital electronic memory. And once again, you would think that we have reached a plateau. There's no possible improvement that could take the place of these micro memory devices, but that limits your creativity and your faith in the growth of technology. That there has to be something. We can either wait for it to happen or make it happen. Just for good measure, I want to point out that not all systems grow according to the S-curve, that there are a number of different types of S-curves or life curves that different types of technologies follow, and I won't get into that because that could be a lengthy discussion. But step one in this theory of directed evolution is first figuring out where you are on the S-curve for your system currently. So let's say you're working for a company, you're in the R&D division or the new technology or the new product division, and it's your job to improve the product line and take it to the next level. Well, you need to appreciate where you've been so that you know where you're going. Okay, so that leads us to these patterns of evolution. I'll point out that there are a number of different versions of this. This is one of the intermediate and kind of more manageable list of patterns of evolution. We covered the first pattern in the second class, evolution towards increasing ideality. We did not cover in any detail the following 6: non-uniform development of system elements, evolution towards increased dynamism and controllability, etc. But we're going to go into those right now. So first, recall, what is ideality? It's the ratio of useful function to harmful functions. Harmful functions is kind of a misnomer. It's not the best word, but it means anything that's costly, whether it's financial cost or resource costly, it creates noise, consumes energy, produces pollution, etc. Useful functions are those that provide some benefit, some useful function, either maximizing your pleasure or your happiness or alleviate your pain. And the key characteristic of any design solution is optimizing ideality. So as systems evolve in a positive sense, typically the useful functions will increase according to that S-curve, and harmful functions will decrease. And that's this principle of increased ideality. So if you were to start with an existing technology and want to improve it according to this principle, you would either want to increase the useful functions, reduce the harmful functions, or somehow increase both or decrease both such that their ratio increases. How do we increase useful functions? Well, we can absorb useful functions of other systems, as we did in the hybridization lecture, or we will if you're getting to that lecture next. We can invent new useful functions, kind of start from scratch with our contradiction diagram and incorporate new functions that didn't exist before. Or we can simply improve the quality or the performance or the parameters of the existing useful functions. Secondly, as far as reducing the harmful functions, the cost, the waste, etc., we can either work to eliminate them, which is easier said than done, but that is in fact an inventive process. We can divert harmful functions to other systems or to parts where the influence is less critical. We can find useful applications for them, as we learned in one of the inventive principles, making a bad thing into a good thing. Or if we can't eliminate them, we can mitigate their impact. So just as an example of the third case, where we're increasing the ratio of useful to harmful functions, I was thinking of a coronary artery bypass graft, or a bypass procedure you may have heard of. In the early days, it was more common to have a triple bypass, 3 blood vessels, because the quintuple bypass was considered to be more risky. But over time, it was recognized that the benefits outweighed the incrementally increasing risks and costs. So quintuples are actually more popular today than they were in the early days of bypass. Another kind of variation of reducing harmful functions is to replace an open procedure where the chest is opened through a median sternotomy using a robot, or what's called a keyhole procedure, where a small thoracotomy is performed. So the advantages there, obviously, is that it minimizes the amount of surgical trauma, the time in the hospital, the pain, the risk of death, but at the same time it also reduces the beneficial effects because there's only so much heart that you could access through that procedure. So it's a trade-off, but it's an illustration of a growth of a technology that isn't quite as good as the preceding technology from an effectiveness perspective, but because the costs are so much decreased, it has a definite appeal. Moving on to the second line of product evolution, the non-uniform development of system elements. It states that each system has multiple components, and that each component has its own S-curve, and they don't always develop at the same rate. So different system components may reach their inherent limits at different times, and that results in contradictions. It also results in a mature component limiting or holding back the overall system. So if you can eliminate the contradictions, that allows the system to continue improving. In addition to the standard separation principles, which you could use to address those contradictions, you could also consider removing
the impeding parts of the system, the parts that are preventing it from improving. So an example, maybe not the best example, is electric cars. They've existed conceptually for decades and decades. Most of the technology, the car itself, the wheels, even the motor and the controls have been mature, and what's been holding back the technology is the limitations of batteries. They are still very expensive, they're unreliable, they have limited capacity. So if we can eliminate that element that's holding back that progress, then we can allow that technology to proceed, the electric car to actually have a place in the market. Or we could just wait, as we've been doing for the past 50 years or so, for the next battery technology to come along. So we can now just ask ourselves, is there really a way to eliminate a battery and still have an electric car? Well, that's the assumption and the reason that we've been stifled up until this day. But if we could just find electricity in some other resource, that might make this concept feasible. And I can actually think of some, but I'm going to leave that to you to try to use your imagination of where we could get electricity from surrounding resources that could make an electric car not require, or at least require as much, the limitations of battery technology. Okay, another quick example, the evolution of luggage. This is something that's kind of amused me as I've been quite a busy traveler over the past 10 years or so. So luggage kind of had its initial burst of growth from the ancient days of carrying a satchel or a bag over your shoulder or on your head to what you might consider to be modern luggage with a handle and a latch. But for quite a long time, that technology stagnated. For, I'm going to say, 30, 40, 50 years, luggage basically looked the same. Maybe they changed color or shape or some of the amenities, but pretty much there was no quantum improvement. And then all of a sudden, you start seeing these upright, wheeled luggages that are initially was used by the flight crew that suddenly supplanted, just completely replaced the ancient luggages. And if you travel today and you go to the luggage carousel, you might see one or two ancient olive green American Tourister luggages, but by and large everything is of this new variety. I'll also parenthetically say that one of the enabling technologies that made this possible, believe it or not, was inline skates, because they gave rise to very inexpensive ball-bearing wheels that could then be applied to these luggages at a very low cost and make them wheelable. So once again, if you can envision the next breakthrough, the next great incremental improvement in luggage, you could be really very rich and famous. Another excellent illustration of this principle is the history of the computer. There are so many components involved in the evolution of this technology, as you know, the memory, the monitor technology, the interface, the software, and these various components have evolved in parallel, albeit at different rates. And as software improves, it forces growth in memory and computing power, and vice versa. And who knows where this cycle of progress will lead us in the near future. The third line of evolution is towards increasing dynamism and controllability. There are two varieties. First is transition to a multifunctional performance. The second, increasing degrees of freedom. In both cases, we start with a prototype or a first generation technology that's static. And in the first case, we introduce changeable elements so as to add additional functions and capitalize on existing resources. So the system becomes variable, and it provides greater flexibility or variety. The second case, we're looking at an evolution in which the system becomes changeable at a mechanical level, like with hinges or flexible materials, etc., and then furthermore becomes changeable at a micro level, like a phase transformation or a chemical transformation, and likewise provides greater flexibility or variety. So here's an example that came to mind. Once upon a time, when you went to the hardware store to buy a power tool, you would either buy a drill or a saw or a flashlight or a radio. They would all be separate products. Today, there is this trend towards these modular systems. They recognize that all of those tools have the same need for power and the same need for a motor. And in these modular systems, you buy them as a set and you exchange the battery pack or the motor driver from one device to the next. So you can mix and match the components to save money. A couple of other examples. When I Googled the words exchangeable, convertible, reversible, configurable, here in the lower left-hand corner is a type of thermometer that is convertible from an oral thermometer to a rectal thermometer to an under-the-arm thermometer. It uses or recycles the electronics and just replaces the thermocouple and the end effector. Another perfect example is the invention of these combination tablet laptops. Or how about the convertible automobile, or a reversible belt or a reversible jacket? Those are all product evolutions that are very clever when you look at them, and you wonder, why didn't I think of that? And I'm saying that you could have thought of it if you would just consciously. Another example of evolution towards increasing dynamism, controllability is aviation. In the early days of aviation, airplane wings were rectangular and they were fixed. And in 1948, Francis Rugolo invented a type of wing that was flexible. It was fully limp and it could change its shape and hence its lift with demand. And today, I'm sure you've looked out your window, you see that most airplane wings are sectional that allow them to change shape under conditions. For takeoff and landing, they have a very curved conformation so as to provide great lift, yet at the expense of a great deal of drag and hence fuel consumption. And then during cruise, they can then flatten out and provide just the right amount of lift for the minimal amount of fuel consumption. Another example from the same discipline are these collapsible wings that become very common in fighter aircraft. It also illustrates another principle of design by analogy, where in nature it's very common to see evolution towards flexibility and adaptability and dynamism. So once again, you could say, okay, we have now optimized the design of the wing. As I've observed wing evolution over the past 30, 40, 50 decades, they seem to be reaching a limit of what can possibly be accomplished. But that again illustrates limiting your imagination to what is currently possible or currently present, and failing to think out of the box and to just accept the fact that there is a new generation that is inevitable, is going to happen. Why not make it happen? Extrapolating that same principle to the field of medicine, since that is what this course is about, I thought about a seminar I just attended last week on the use of these steerable catheters and steerable surgical elements. So not too long ago, the scalpel was a very static instrument, and it had evolved over 100 years, looking pretty much the same as it did when it was first introduced. And now today we have these snake-like robots and these steerable catheters that is promising to revolutionize the way surgery is performed. So in summary of what we could do as far as increasing dynamism controllability, with respect to dynamism, we can improve the ability to change and adjust to multiple conditions or requirements, meaning we decrease the degree of stability, You can transition from a stationary to a mobile condition, which is pretty obvious. Divide a system into mobile parts. Remember segmentation. Introducing a new object that's mobile. Apply different physical and chemical effects to different regions, separation in space. As far as controllability, if you introduce a field, either one that's part of the environment, a resource, or one that you introduce intentionally, you can introduce controllability. Introduce a controllable additive, a controllable anti-process, a self-control of the system, or garden variety feedback. Here's a particularly clever use of fields to introduce dynamism. It relates to the harmonica, which is an instrument that hasn't changed pretty much for the past 100 years. It involves a flexible reed that's usually made out of brass, the frequency of which is governed by the stiffness of the reed and its mass. Well, by introducing a magnet in the proximity of the reed and then using a reed that is paramagnetic, it's possible to alter the pitch of that vibrating beam and consequently introduce what amounts to a whammy bar effect to the harmonica by simply pressing a button and moving the magnets around. Moving on to the next line of evolution, increasing complexity followed by simplification or reduction. It reminds me of one of my favorite quotes. All things are difficult before they are easy, which is attributed to Thomas Fuller. And it is never more true than in the evolution of technology. The most brilliant inventions, the most clever inventions are often the simplest, but they often derive from a more complex predecessor. So there were a number of simplification methods that were introduced in the textbook. I'm not going to read them all off to you. We're not going to go into great depth. You can read them for yourself and utilize them as you see fit, as you aim to evolve or improve upon your. One of these methods is known as segmentation and integration. It relates us back to one of the 40 inventive principles. And again, I'm not going to read these in great detail. I'll let you read them for yourself. And then consider them as you are trying to find innovative ways to create a new version or future embodiment of an invention that seems to have been stagnant. In the textbook, they go into great detail introducing this concept of a bi-system or polysystem. And I'm likewise not going to go into great detail here. You can read it for yourself and apply the principle as you see fit, either in your term project or in your future career as you are pressed to try to innovate and improve and evolve a product into its future generation. The fifth line is called Evolution with Matching and Mismatching Elements. Here it's based on a premise that system elements are matched or mismatched to improve performance or to compensate for undesired effects. It's a little bit related to separation principles in that in matching we may make parameters equal or proportional or mutually dependable. In mismatching, we might do this to counteract a harmful effect, so to make the related parameters different or independent, or for that matter, dependent and opposite. And then the fourth version is kind of like the previous ones, but in which the separation is under conditions. So the matching or mismatching is something that is dynamic or changes with the need for this function. And they give you a list of parameters that you can consider as you're trying to enumerate or explore opportunities for matching as mismatching, like the system structure, its temperature, its strength, its magnetic properties, etc. I'm not going to go into great detail because there's just too much information for the amount of time we have. But there is an example that uses a car suspension. If you're familiar how it works, all the better, because you'll appreciate that this exhibits unmatched elements in that the springs are attached between the wheels and the body. There are matched elements in that the shock absorber and the spring are connected, but they're serve very different functions. One is an elastic function, the other is a dissipative function, and they work together to damp out impact. Mismatch elements is the semi-rigid rubber isolation, the bushing between the control arm and the frame. And then dynamic matching mismatching is what you find in fancy cars like Mercedes-Benz and Cadillacs that has automatic compensation to adjust for road conditions. Example of integration, this is, I think, a close cousin to hybridization. You may have noticed that in the stores, if you go to the hardware store, ever shop for a shower head or handle, that it's now popular to have these combination handheld shower, conventional showers. Whereas these used to be two separate products or two separate items, they are now integrated. And it's become almost the standard. You can't even find the old-fashioned type of shower. It's another illustration that a brilliant idea comes along after tens of years of no change, no change, no change, and suddenly everyone is copying the idea because it was just an idea that was waiting to happen. Didn't require any breakthrough in science or technology. It was just someone having a brilliant idea, demonstrating a market need, and then running with it. The sixth line of evolution is evolution towards micro level and increased use of fields. It's arguably one of the most difficult to understand, but also one of the more powerful. It's illustrated in this flow chart, where we start with an existing technology or invention that exists on the macro level. And then it evolves into becoming a polysystem, something that is made out of subsystems, that has movable parts, it has simple shapes that are interrelated. It further then may be evolved into something with smaller and smaller elements, such as small particles or powders, etc. At which point, the use of the material structure can be used to provide more functions or eliminate harmful effects. And the use of chemical processes, not necessarily in that order. But then it allows the use of atomic level forces and phenomena, and hence the use of energy fields. So these steps aren't necessarily sequential, but they are hierarchical. A really simple example is presented in Dr. Zussman's presentation relating to cooking oven development. So once upon a time, cooking was done in a very inefficient cast iron wood-burning stove. And then around the 1930s or so, natural gas came into play, which introduced a reduction of the scale, not in an obvious way, but in kind of a subtle way, replacing wood with a gas. That was then replaced by electrical stoves, which then gave rise to toaster oven, etc., which then gave rise to microwave ovens, which is something that occurs on the atomic level. I can think of the same thing with respect to imaging that evolved from X-rays to MRI, magnetic resonance imaging. And there's definitely multiple examples. Here's an interesting thought experiment. Clothing, something that really hasn't changed essentially since prehistoric times. All clothing today is basically a variation on the same theme, and there is a huge variety of it, but it's all based on the same technology. But we know clothing is far from perfect. It wears out, we get tired of it, creates a huge amount of waste, a huge amount of resources. So I argue that this is an unsustainable technology, that it is ripe for evolution. And if I were to ask you to try to envision clothing of the future, what would it look like? How could you use evolution to the micro level to envision the future of clothing? Well, what is clothing? It's made out of fibers. So rather than weaving fibers into cloth and cutting the cloth with scissors and stitching the pieces of cloth back together again, is there another way we could manipulate fibers so as to create what amounts to clothing? Well, I kid you not, there is a laboratory that is actually developing spray-on clothing that could be recycled and used over and over again. If you click on this link, it should take you to a YouTube video, and I think you'll be surprised how close to like reality and how feasible this might actually be, as odd as it might sound. Here's an example from my own discipline. Once upon a time, there was an artificial heart. It was designed to look like and function like the human heart. It had plastic ventricles, it had carbon valves, it beat in a pulsatile fashion like the native heart. And it worked for a while, but it was far from perfect. It had many imperfections. So then it was realized that the pumping function could be performed in a more efficient way using a different type of technology, a turbine type of technology known as continuous flow. It was much smaller, had one moving part, and was less prone to the many complications of the old-fashioned artificial heart. But now on the workbench and in the pipeline is the idea of turning to the micro level, of recognizing that the heart muscle is made of a heterogeneous collection of cells and connective tissue and blood vessels, and they all perform important functions. So the future of the artificial heart is now in trying to reproduce or replicate this cellular structure so as to create basically an artificial heart muscle. So this is what has given rise to this latest trend or fad of tissue engineering, whereby any number of biological tissues are envisioned to be reproduced or grown in the lab on scaffolds to replace the function of the disease tissue, but not on a macroscopic scale, but on actually a continuum of scales that involves metabolism and vasculature and uh, control and all of the many functions that our tissues perform. And just one final illustration reminds me of many years ago when I was on the organizing committee of the American Society of Artificial Internal Organs. Believe it or not, there is such a society. They had asked for suggestions for topics of future meetings. At the time, there were artificial hearts and artificial lungs, and I felt that it would be interesting to explore the use of nanotechnology in our discipline. And it was something that was really unheard of, because at that time, everything that was invented was on a macro scale. It was a replica of a lung or a kidney or what have you. So they looked at me like I was from outer space, and it went nowhere. 10 years or 15 years later, I can't remember the time scale, it's now the latest craze in artificial organs, is using nanotubes and nanotechnology and piezoelectric materials to produce the next generation of this field. And I'm bringing this up not to illustrate how brilliant or insightful that I am, but how difficult it is to introduce the next generation of an idea when it's not obvious, when everyone is thinking that we've already maxed out our capacity, that we've reached the plateau, there's really no room for improvement. It's incumbent on you to try to illustrate that there is room for improvement, and there is a natural trend that has been proven through history to follow these lines of evolution. So either you get on the bandwagon. The last line of evolution is towards decreased human involvement, and it's almost an obvious line of evolution. It's what we think of when we think of progress or technology. It involves systems that develop to perform tedious functions that free people to do more intellectual work. So one of many examples is a clothes washing machine that used to be a manual operation that involved a tub and a washboard or beating your clothes against a rock, and was replaced by the wringer washing machine and then an automatic powered washing machine, and now a modern washing machine that does everything from adding bleach and fabric softener, and I think there's even now a washing machine that does the drying. And if there isn't, then that would be the obvious next step in the evolution. Why would I need both a washer and a dryer side by side when I can hybridize and combine those functions and remove a step? In the textbook, there were a number of helpful hints for replacing humans with machine. Again, they're somewhat obvious. I'm not going to read them for you, but I just want to make you aware that there are some guidelines. And they're broken down into a number of different categories, not just in replacing or improving mechanical devices, but also in control and decision making. So in summary, when you consider the many lines of evolution, you consider a current state of the art, or we can say prior art, there are many different dimensions in which the technology can evolve or can improve. And by intentionally and consciously trying to grow along each of those different axes, you could really get an advance on your competition to develop the next generation, and maybe even the leapfrog to the next generation. And from my perspective, that's the fun part of engineering, is the creative part of thinking and creating the future. So when we talk about this idea of directed evolution, the whole point is replacing trial and error with a intentional, directed, algorithmic set of steps to improve. So as technologies evolve, there are various bifurcation points where decisions can be made. And you could arguably go off in all different directions, some being the wrong direction and some being towards improved ideality, improved autonomy, etc. And this is a kind of an illustration of replacing that trial and error and guesswork with a methodology. And just to kind of also illustrate that the course of history, think of the history of aviation. There are many different divergent ideas of what an airplane should look like, and not all of them survive. And consequently, a lot of just wasted effort and life and limb was expended as a result of this painful process and inefficient process of trial and error. So speaking from my experience, I was once asked to give a lecture at a conference about the future of rotary blood pumps, artificial heart technology that was in vogue. And as I looked at this assortment of devices that was currently under development and the large variety of solutions to the very same problem, it made me recall the history of aviation, and likewise the many divergent paths that were taken until all of these paths converged on one optimal solution. And in so doing, I think I was able to make a point that ultimately there would have to be some consolidation and some convergence of ideas. So in summary, these are the steps that are generally involved in implementing this directed evolution methodology. First, you need to know where you're going. You need to define objectives, hence by introduction of the objective tree early in the course. Second is understanding where you are presently in the S-curve, understanding the current vision, the perceptions, what is the market, what are the enabling technologies that can be harnessed, existing functions, and the resources, as well as the potential failures. Then by researching the past and understanding evolutionary patterns, you can now begin to envision the future using the various lines of evolution we just learned about. At that point, you can define and imagine an ideal solution or ideal direction to pursue, which of course is not going to be easily realized or practical, which means that you'll have to deal with the contradictions. And we address those using the tools that we've learned through TRIZ, using the ideation methodology. At some point, you need to make decisions that kind of trade off between the costs and the risks and the failures and the rewards. And you need to remember, as you're inventing, to protect your intellectual property, So applying the appropriate strategies to allowing yourself to operate and to build fences. And then ultimately, obviously, what everyone knows how to do, and the steps that often take the most of our attention, is the implementation. And recognizing that new problems will arise, auxiliary problems, and then dealing with them, as well as dealing with potential failures that may crop up as you try something new. Just for the sake of completeness, I want to point out that these lines of evolution I just presented is but one version or one subset. If you go back in time to Altschuller's original theory, he had 8 somewhat different lines of evolution, which you can explore on your own if it so interests you. And I'll also point out that Boris Zlotin and Alice Zussman have evolved their own new set of evolution lines that are actually very numerous, broken into these 7 groups. And I don't even know what they all are, but they put a lot of effort into it. And if this is something that appeals to you, or maybe somewhere down the road in your career, you're in charge of product innovation, you might want to return to this as a resource for breaking out of the mold of doing things the old-fashioned way. So if you permit me to wrap up by returning to levels of invention and pointing out that this whole theory of directed evolution is about giving you the tools to think outside of the paradigm, moving away from putting new coats of paint on old technology, remanipulating existing components and resources, but actually taking advantage of enabling technology, latest discoveries, to invent outside the paradigm. And finally, keep in mind that timing is everything. If you look at the patent literature, you just look outside your window, you see that innovation is happening very quickly. So it's essential to recognize the opportunities when they occur, when all of the components are present, so that you can capitalize on them, jump on them, and beat your competitors to the reward of having innovated the next generation. So thank you for your attention. This was a relatively long lecture. The subsequent 3 lectures are really short, I promise.